Can have one of the mics.
Can I bring Sophie a gift on my way by tonight?
Check, 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 check.
You gonna steal the microphone? Sweet.
All right, everyone. Good afternoon, and welcome to today's EOL Seminar. Thanks for your patience with the glitches, happen sometimes. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Michael Gallagher. Dr. Gallagher is a research scientist at the Cooperative Institute for Research in Environmental Sciences at the Physical Sciences Laboratory. He works to improve in situ climate observations for analysis and applications. In recent times, he has worked in collaboration with other PSL researchers to refine a mobile research platform to make real-time autonomous observations of surface energy budget, turbulent exchange characteristics, precipitation, and cloud properties, as well as their connections to changes in the subsurface. These platforms have been deployed to locations across the globe, from the Arctic to the Splash Field site in Crested Butte, Colorado. Michael is passionate about reducing the cost and size of observation platforms, improving the quality of data products available for model evaluation and other applications, as well as new methodologies for analysis of observed physical processes. Please join me in welcoming Dr. Gallagher for a seminar on how Greenland melts.
Thanks. That's a really great introduction. The way I talk about the work that I do, I think I'm kind of a hardware engineer disguised as a scientist. And I don't know about the backgrounds of everybody in the room or online, but I'll try to give you a little taste of all the little pieces that we do. So if you're interested in the hardware and the more applicable side of things or the deep science side of things, we might be able to talk a little bit about all of it. I think I submitted a pretty salacious title. I said how Greenland melts and then put some words after it. But what we really study is how Greenland changes. So we make a bunch of different observations, and the idea is in high time resolution, how is the Greenland ice sheet changing and why? And what is it connected to? And then because I'm just not quite a scientist, but more interested in the observations, I think of it as a platform. So how can we build something that can be used in all sorts of settings and places and things like that? And the thing that we built ended up being a modular, highly applicable piece of instrumentation that we're hoping we can convince a lot of people to use at some point. Since I don't know any of you very well, I don't even actually recognize anybody, which is kind of crazy. I've been in Boulder for about 10 years. I'm a series research scientist at NOAA, so I sit at PSL just underneath the Flatirons there, and I have a window facing the other direction, so I get to be sad. But our mission is to form a unique bridge between observations, process understanding, and modeling. So a lot of what we choose to do is based on those last two things, process understanding and modeling. So how can we evaluate models? How can we get observations that let us better evaluate models? And what's wrong with models? So it's not just observations for observation's sake, but how can we make those to inform those other sorts of things? My personal interests are pretty specific to Arctic and Greenland science. So if you don't think much about how the ice melts up there, I might say some things that you don't quite connect with, but things like atmospheric dynamics and transport, boundary layer characteristics, exchange processes. So if you have snow falling, how does that exchange with mass, or how do you get sublimation? Those are the sort of science questions that motivate me. And then, of course, it wouldn't be a talk in the 2020s if I didn't mention machine learning at least once. I like applied algorithms. They're fun to look at. And then my team's emphasis is doing all of those things with autonomous observations. And probably the most novel thing I'm going to talk to you guys about, and the thing that is different in Greenland that we hadn't really done before, is this renewable power system component of it. So this photo is a photo of an earlier prototype that we built in the sea ice in the central Arctic. But the one in Greenland was deployed on fully renewable power on its own kind of modular microgrid setup, if you are interested in that kind of thing. Feel free to interrupt. I'd like interruptions. If I'm missing some big chunk and everyone's not paying attention, then it doesn't help anybody. So you're welcome to poke me if you need to, and I'll try to stick to the broad appeal for you guys all. So why Greenland? Greenland is kind of meteorologically unique. It's got very unique atmospheric dynamics and transport. Its melt events have a real fingerprint. In a lot of places in the Arctic, you get a wide variation in terms of what extreme melt looks like, but Greenland extreme melt kind of follows a very typical pattern. And it's weirdly simple. You have a dome-shaped ice sheet inside of the North Atlantic there, and there's not a lot of other topography. It's a large topographic dome. So if you get transport, it hits the ice sheet, it goes up the ice sheet, and the physical processes are relatively easy to understand. So if I was pitching you on the Arctic side of things, I think that makes it kind of like a little mini science experiment in its own right. It's not like trying to do research in the mountains here where you're like, oh, we don't know what's happening and why. And I'm sure you all know a lot more about that than I do. But another reason is that Greenland is the fastest melting piece of ice on Earth. It's the largest contributor to sea level rise by far, and it will continue to be as the Earth warms. And who doesn't love a good challenge? If you build hardware and you're interested in building hardware, you can take it to this really nasty place. And where we took these, those are the 2 dots on the map there, it melts a lot. So you'll get snowfall, it'll be minus 40, and then it'll be above freezing, and you'll get water. And water that melts and refreezes is kind of a nightmare if you like to build things that work. So this project was called ICECAPS Melt. It was an extension of a long-running project that I've been working on as a contributor to for about 10 years, but the project itself is, I think, going on its 15th year or something like that. The ICECAPS team, has made observations in central Greenland for that long, but the idea is we've learned a lot, and we want to take it to where there's a lot more melt. So there's not much melt in central Greenland, and we want to understand melt. So we're kind of moving down the ice sheet. So MELT is a fancy acronym. I'll define it in a little bit. But the 2024 campaign was a complete in-house prototype for in situ coupled climate observations, this custom renewable energy power system that I mentioned. And maybe the biggest component of it is autonomous operation and control. So you set the thing out, and then it can do feedback. You can talk to it. You can say, hey, that's using too much power, or that's broken, and you can turn it off. And so you have real-time data and diagnostics. So if you were like, hey, Michael, can we evaluate the energy budget from yesterday? I could have given you that data. We had a web page you could go to, and you could look at the full timeline as the data streamed in, which is really novel for Greenland in particular. And then number 5 was kind of, I wouldn't call it an afterthought, but it was maybe the least important part in terms of getting this project done. But the idea being, if you make it modular, if you make it plug and play, then you can use that work more later for other projects that have different applications. It's the first of its kind, which is, that there's always precursors, and that's a very bold thing to say, but it's never actually the first of its kind. But it was the first time that something this large has autonomously operated in Greenland, as far as we can tell. It's a lot larger than an automatic weather system, these stations that people put out to make basic meteorological observations. The power system is in the lower left there, so that's the kind of our little version of a Tesla power wall. We engineered all of that. It's about half the size in terms of total battery bank of a Tesla car, so it's pretty dang large. That's about as tall as me. And I'll give you some more stats on that when I talk specifically about the power system. But the goals, the science goals, so separate of these kind of engineering goals, were to get a complete summer of operation, if we can get a whole summer of data in a really melty place with all of these complex things, that's great. To be sure we get system communications and we can actually control autonomously in the way we claim to, that would be really great and be a little gold star on the side. And then if we can get information for future deployments, so if we do have failures, why did we have them? It's a prototype, you do learn things and things break, and things did break. And then if we're lucky, we get to eventually do research. And as a hint, we did get lucky and are doing research right now. I'll name some of the critical folks because you might know them. There might be some names that you know. This project definitely wasn't possible without this list of folks and a whole lot more, honestly. But these are the folks in Boulder, with an exception of the bottom two, Chris Cox and Matt Shoup, who have been at NOAA for a very long time and doing this kind of thing, contributed a significant part of this. Ann Sled, who's a bit newer to the Boulder scene, is also at Ceres sitting at NOAA. And then those two folks, Ryan Neely and Heather Guy from Leeds in the UK, also put a significant amount of effort into this summer campaign. So to explain where we were and what we were doing in a really broad way, so hopefully I can pull you all along with me. The map of Greenland on the left, the two dots are the sites where we operate instrumentation. The blue dot is Summit Station, if you've heard of it. It's the central station on the ice sheet. It's operated by the NSF. It's pretty large. It's got a lot of structures. There's people that live there year round. In winter, there are 6 people that monitor the station, and they monitor our instrumentation. So if something breaks, we have spares. They can be there to fix it. And the red site is a place called Raven where there's nothing. It's called Raven, but it's just a place where you can land a plane, and people regularly do, so it has a name. And that's where we installed the instrumentation and the platform that we developed this last summer. It's about 140 kilometers from the very edge of the ice, the nearest edge of the ice right there. The contrast on the screen's a little wonky, but that 140 kilometers is about 70% deep crevasses, moulins. It's really in the heavy melt zone, and we're just above it. So you still see a lot of melt, but not enough to get deformation and the other nasty processes that kill scientists and you want to stay away from. This is a snapshot of our camp. So this was the spring install. So we've got the left side there. We've only got about half of our solar panels up. We installed 16. So this photo was taken about halfway through the install. It was 2 weeks of minus 40 weather building those solar panel configurations you see there in the instrumentation. It was the 5 of us there, Matt Shoup, myself, a graduate student named Andrew from the UK, Kat, who is an engineer that we worked closely with, and Vaughn Walden from WSU in the Northwest, Washington State. And this is a little bird's eye view of our camp. So if you've never thought much about Greenland, it's a lot of flat white. The thing that I tell elementary schoolers is it's 3 times the size of Texas. It's this really large, flat, white piece of ice, and it's 11,000 feet tall. So when you're there, it's this vast barren expanse, and we were a little blip in that, and we were completely self-sufficient. We cooked all of our food off of our own renewable power system. We built everything ourselves. We just got plunked out by a very large C-130, these Air Force planes, which is a big part of this. Logistics plays an interesting role, and I won't talk too much about it, but how and where you go has a lot more to do with how easy it is to do, not whether or not it's the interesting science. So, MELT stood for Measurements Along Lagrangian Transects. It was an extension of this long-running ICECAPS projects. And this area that we went, that red dot, Raven, is the percolation zone. So it's above where it's melting all day, every day, but water is still regularly occurring and percolating down into the firn or into the upper layers of the ice sheet. And the kind of driving science question I've danced around a little bit is, what is the fully coupled climate? Can we measure the fully coupled climate where it melts in the percolation zone autonomously? So can we build this, and then maybe we could do it more in the future? The measurements characterize things like clouds far before they got to summit. So the transect, the idea is that there's this melt pathway that goes up the southwestern coast there, and we want to measure clouds before they get up on the ice sheet, because that has important connections to the coupled climate. How those clouds are connected to the near surface atmosphere, and then the real atmosphere surface coupling, like skin temperature, these sorts of things, pinning down those really tightly. And then impacts on the upper 3 meters of firn. So you have that upper 3 meters of ice sheet. We did profiling with things like thermistor strings, ground penetrating radar, and all of that so that we could characterize the evolution of melt events, both in time and in the vertical at this point. And there's a lot more. It's a really large platform. In one of the next slides, I'll name all the specific instrumentation. But I think I counted a total of, depending on how you count, 92 sensors. And that's including things like a ceilometer, which is a pretty large sensor. So this is a list of the really critical variables, or at least the ones that folks in the room would probably know. And this is a time lapse. There was a camera system that we built for it. So we have 4 cameras that took pictures at intervals of 15 minutes so that we could evaluate the states of the instruments so that we could see the conditions. There's this really fun thing when no one's out there actually looking at the sky. You might be like, oh, the instrument says it's frozen, and then you have this picture where it's just tipped over in the snow or something. So photos tell you a lot. I love photographs. And while that runs through, you can see I'll restart it just for giggles. You can see the turbines spinning in the background. And actually, this is while we were building, so you can also see little folks running around there. But we measured the full suite of surface fluxes, the complete broadband radiation, diffuse and direct, meteorology, turbulent fluxes, surface height variability in 3 different ways so that we can understand the spatial variance of those kinds of things. Infrared temperature in a couple different ways also, so we could get some spatial variability with different footprints. Subsurface measurements with temperature and radar reflectivity and energy fluxes. We have little plates that we can insert into the subsurface and know how much energy is transferring into there. And we then also derived skin temperature using the long wave fluxes from our broadband measurements. Other really important observations, and maybe what is most novel about what we did, we had these really high power things that you probably have all heard about. If you're more on the science side of things, we had a precipitation radar, an MRR Pro. We had a depolarization lidar sort of thing, ceilometer, the Vaisala CL61. We had a microwave radiometer, which, as far as we know, is the first time anyone has operated a radiometer autonomously in the Arctic. So it's a pretty complex instrument. It's got these tipping calibrations and a whole bunch of moving instrumentation components of the instrument. And it operated for the entire time frame that we took measurements. And then we did a bunch of other kind of sampling measurements. We used a drone to do surface roughness of photogrammetry so we could relate things. Snow pits and site surveys that would complement our understanding of the subsurface. We had an aerosol spectrometer, a POPS that is actually developed up there in Fort Collins, and then the cameras, like I mentioned. Oh, now I'm out of the thing. These are just some photos from other experiments. I think it's important to acknowledge that this is the thrust of a lot of stuff that we've all collaboratively worked on. So the team that I work with, a lot of us developed instrumentation for Mosaic. It was this drifting campaign in the central sea ice in the Arctic. That middle photo there is a buoy that we've worked on in collaboration with ONR, the Office of Naval Research. We've put a bunch of instrumentation on and developed some of our code and algorithms for autonomous operation. And then the lower photo there is an even bigger buoy. That thing is, I can't remember exactly how long. It was like 45 feet long that we also worked on with ONR. So all of this effort is kind of the, pinnacle, the height of these efforts. We've taken all of it and put it together and tried to glue it together specifically for the Greenland project. Some more photos just to show you what we got up to. We had all of that battery bank and we buried it in the subsurface to try to keep it warm, which is a little counterintuitive, but snow has high R value, very insulative. And so burying the batteries keeps you from taking a lot of that energy away. And if you have to heat your batteries, we used lithium. I could talk about that choice for days. It was risky. It ended up paying off. So each of those engineered little battery boxes has a little heater, ceramic heater in the bottom of it that we programmed and had feedback loops with. That's the assembly of the panels with the instrumentation system in behind on the top right. Those are the wind turbines that we deployed that ended up being a total failure, if I'm being honest. We got power for a good month and we knew they would be, but we wanted to test some new ideas anyway because we're masochistic. And then that's the whole platform itself with the different instruments. In the foreground, you have the firn sampling, and in the background, you have some of the profiling for the atmosphere. So the power system we developed ended up with the name MVP, which was an acronym for Minimum Viable Power System. If you've worked on power systems, this doesn't look too minimum to you probably. And it ended up not being very minimum. We were a little afraid of failure. It was 30 kilowatt hours of storage. So you could run a kilowatt of power into different heaters and profiling instrumentation for more than a day without any power input. And it was 8,000 watts of solar and 1,600 watts of wind if it had functioned the entire time. It was fairly large. It was myself and one of our engineers spent a whole lot of time designing it. We learned, and this was a great thing to learn, and we kind of hoped this is what we would learn, that we could get away with about half of that, both in terms of storage and solar generation, and still have been fully operational. The core of it, I've mentioned this a couple times, is that it was modular. So each of those batteries could be unplugged. If you get to the ice sheet and something got kicked out of the plane and broke on the way there, you're in luck. You can just unplug it. You put a little blank in there and you can run with 19 batteries instead of 20. Or you could, in principle, swap out connectors. And the whole thing was designed to be kind of these Legos for power. We had power products, so you could look at any of the variables related to what the heaters were doing, how the batteries were doing, how the inverter was doing for operating the profiling instrumentation at any time on the scale of, I think we ended up averaging out to 10 seconds. So you had production history, you could do projections, you could, if you had something wrong and this happened, if you have an instrument short out, you could sense that and you could then try to troubleshoot remotely, which was extremely helpful. This is new to me. I've been making these sorts of measurements for 10 years, and being able to do that is like a dream. It makes things a lot easier. These are some plots from the renewable power system. I won't tear you through them in ugly detail, but the top is the batteries, the middle is the actual power generation, and the bottom is the output to the instrumentation, so the actual usage. There's a bunch of nuance in here. If the batteries are 100%, then you can't charge them. So the renewable power then will follow your instrumentation curve. And then as you start to drain the power down at night, that generation goes to both your power or to both your batteries and your power usage in your instrumentation. We would use about 10%, in the bottom one there is a 24-hour plot. We would use about 10% of the battery bank at a night and typically recharge nearly back to 100%, so long as there wasn't problems like freezing or snow cover, which we did have. So the bottom plot is like a best case scenario for our power production. And then I'll give you some science highlights and hopefully we can have some time for questions. These are very, very preliminary. I'm working on a paper right now to highlight all of what we actually did in all its gory detail, but this is just gonna be some fun little bullets. So the thing that I'm personally very, very interested in is the subsurface energy transfer. So you have things like sunlight or cloud temperatures or advective transport, and it has a certain impact on the ice sheet. And you want to measure how much of that energy goes into the surface and where and why, or when it leaves the surface and where and why. And if that happens because of wind, for example, via turbulent exchange. And we got a complete time series through the summer, which was just so exciting. There was a lot of honestly luck involved in that. Sometimes things just don't go wrong, and that's lucky, and sometimes they go very wrong, and that's bad luck. I think in some ways we got really lucky. It wasn't a very melty summer, which meant we had to deal a lot less with water ingress, which might have been part of the luck. But our data comes in at 1 minute resolution roughly, and we get some statistics on that. But in terms of most of our variables, it's on a minute cadence. And we're going to put together a detailed evaluation of our percolation events, the melt onset. So when we arrived, it wasn't melting. We arrived in early March, and then melt began, and we watched that transition season. That was really exciting, and we're going to characterize that. And hopefully we'll also be able to do a full mass budget. So the hydrology, you have snowfall that goes in, and then you have this percolation of melt out, and you can do a mass budget of that. The plot on the right is some of the core variables that I think most folks would be interested in or understand. So on the top, there's two temperatures. There's the air temperature there in blue and the skin temperature, so the temperature of that surface layer in purple. And you can see the diurnal variability there for the full time series. The second box below that is what we call the flux plates, but that's the energetic flux in the subsurface. So we installed flux plates that measure in watts per meter squared the energy transfer through layers at 25 centimeters, 50 centimeters, and 75 centimeters. so you can watch the different responses in the different layers to the energetics at the surface. So for folks who don't look at these plots all day, you can see the temperature vary on the top plot there, and then you can see the energetics in the subsurface respond differently depending on which layer you're looking at and how near it is to the surface. The bottom plot there, that's those color contours, is our subsurface 3-meter long temperature string that has a 2-centimeter resolution. So it's a really high resolution temperature string buried into the firn. And we can then also do things like calculate conductive flux and things on a really high vertical resolution that relate to those flux plates. The reason we have both is because there's some flaws with having temperature strings. You can imagine if you get melt, you might have that water that just channels along there. And it's a very real issue, but you want to take that measurement anyway for reasons that could be, well, I could explain in all their gory detail. But my favorite feature is the hysteresis with depth. You can see like an energetic impulse warming in the daytime. You can see it reach that first layer at 25 centimeters, say before evening sets, and then you can watch that impulse accumulate over time in the very deep subsurface and that temperature increase. Like I said, we could hash one of those sentences out for 25 minutes, but these are some things to look for in there. And if you have some questions about it, I'm happy to answer them at the end. Or now, if they're really pressing. This is the melt onset plot. So this is, you can see it's the same measurements in the same order. So you have the temperature above in the atmosphere, you have the flux in the subsurface, and then you have that thermistor string. I've plotted it a little differently because I think this is more intuitive. So the color is now the depth down. So you can see the low or the temperature sensors that are higher up, that are close to the surface, very, very rapidly. The temperature changes really rapidly, and the ones in the subsurface hardly change at all. And you can see the energetics that I'm talking about. So when the temperature in the air goes up, you see the temperature in the near surface go up pretty rapidly, and then you see this increase in temperature in time and the spreading out of those lines as you get into June. It's a bunch of fun stuff to look at. I think it's really exciting. I think I put this as the coolest figure I've ever made. I kind of believe that. I don't, it's also because I'm new to it. It's always really exciting to look at something new that you've been thinking about and never had a chance to look at. Oh, I hit the wrong arrow there, sorry. There we go. So these are our cloud measurements. These are from the depolarization lidar. That's the Vaisala CL61 ceilometer. One of the ways that we're still hashing out how we're going to frame the paper. I think an interesting way to look at energetics in places like Greenland is in terms of albedo. So albedo is the reflectivity of the surface. Snow is white. It reflects a lot of sunlight, and that has a certain impact on the way that the energy transfers into the subsurface. But albedo itself, the reflectivity, evolves in time. And you can imagine if you get snowfall will increase that albedo. It'll make the snow more white, and that will change how the energy transfers. So there's these sort of feedback loops where if there hasn't been snowfall, albedo will decrease, and there will be a lot of sunlight that gets absorbed, and then you'll get a snowfall impulse, an event, and then all of a sudden you'll have very white snow on the top surface, and now you'll start rejecting a bunch of sunlight, and this evolution affects the way in which the surface evolves. So this is just on top is the attenuated backscatter, so nothing processed or fancy from the LiDAR. It's just basically a proxy for how thick the clouds are at those heights. And then the bottom plot is the albedo from our surface measurements. And so you can see the variance in the albedo that relates to different processes, and you can connect it to clouds. Now, for folks who haven't thought about Greenland a lot, that might be a counterintuitive thing. You're like, why would I care about how clouds relate to albedo? One bullet point there is the snow, like I'm talking about. If you have clouds, you have snow, which modulates your albedo. But I would say, in my opinion, the most pressing open science question in Greenland is how clouds connect to energetics. So moisture is very uncertain. The model parameterizations of those things are uncertain, and moisture transport comes with a lot of energy. Clouds are typically warmer than the atmosphere surrounding in the Arctic. And so if you have clouds come in when it's low albedo, that has a very different impact than if clouds come in on high albedo. And so this plot shows the interplay there. Now for a paper, we'd have to do a bit more analysis, but it's one of the things that I wanted to point out to you all. This is the precipitation, so it's the same figure on the bottom, the albedo, but on top isn't clouds anymore, it's the precip radar, so it's actually measuring snowfall as it comes in. So this is a bit more one-to-one. You can watch snowfall events happen, and then you can watch the albedo shoot up after the snow reaches the ground. So I'll point with my mouse a little bit, a couple of them in here. This is a really fun one. The albedo tanked here because this was one of our first melt events on the 3rd of June. So the melt changes the crystal structure of the surface, which changes how readily it can absorb sunlight. And then almost immediately after the melt event, we had these snowfall events that lasted, I think, like 3 or 4 days. And you can kind of see that on the axis there. Dumped a whole bunch of new snow, and our albedo shot back up again, which meant we were unlikely to melt for a while until that structure changed, unless we got a really extreme transport event. And you can see these happen throughout the time series. This is another really fun one. We had a lot of clear sky in mid-June, and you see the albedo start to tank again, and we had a very large melt event, and it really went low. 0.78 is a very low albedo for the Greenland ice sheet. And then you had our largest precipitation event almost immediately thereafter, and this quenched the melt again. So lots to point out. I'll continue to gloss over these things, and hopefully you can ask questions of the things that are particularly interesting. I told you no one's operated one of those microwave radiometers in the Arctic autonomously before, and it's definitely one of the most exciting things. So I wanted to show you some of that data and talk about it just a little bit. Like I hinted at, and I'm sure as you all know, clouds have a temperature, and that temperature has a black body radiation, and that has an impact on the surface. And these microwave radiometers measure the brightness temperature of the clouds. They give you an idea of how warm and how thick, how juicy they are. So you can watch the evolution of the juiciness of the clouds and perhaps the long wave impact on the surface. So on the top is an unprocessed brightness temperature from the radiometers. So where you see spikes, that's probably cloudy, juicy cloudy times. And on the bottom is the 2 temperature variables I was telling you about, the 2-meter air temperature and then the temperature of the surface derived from the long wave. And you can watch a similar interplay happen. And there's some subtlety in here that'll be hard to point out to a not Greenland audience. You could imagine that because the Arctic is pretty cold and dry, that you only get warm clouds when you only get clouds when you get warm moisture transport. And so there's some interconnectedness in terms of how these events evolve. So you'll see the temperature shoot up here where it's really cloudy. That's not necessarily because the clouds were solely responsible for that temperature rising. It's also because transport occurred. And that interplay is one of the things we want to understand. And it's one of the things that models are really bad at capturing. Well, that's too strong. That models struggle to capture. And as I continue to hint at, all of these things are connected to synoptic transport. You can do really fun things like Lagrangian analyses to try to tease out what came from where. Yep, and then this is the salometer data overlaid on the same thing. So you can imagine you could look at events in holistic characterization, where you have these brightness temperatures, you look at the energetics of the clouds, and then you can come in and you can look at the detailed characteristics of the clouds. Where were they thick? Why were they thick? And those sorts of things, which in Greenland for autonomous observations is a really, really exciting thing. Okay, and then the final thing I'll talk to you all about is the snow and the firn and the subsurface. And I'll admit to you all right out the gate that this is what I specialize in least. So we have a snow science team. I'm not a leader on the snow science team. And they put together a program that would help us take all of the measurements appropriate to understand how the atmosphere connects to the subsurface. And then the snow science team made those measurements. So I'll tell you what they were, and I'll talk about them. And I think there's some really neat, exciting things in there, but I'm not trying to claim I'm in any way the expert on that. So the atmosphere is connected to the subsurface. It's coupled to the subsurface, and it's coupled to the subsurface through the characteristics of layers. If you're a backcountry skier, you know that really well. If you have a very thick ice layer, that's going to have a different conductivity, a different structural integrity than the layers below it, and that's going to mean something for how energy transfers, how water transfers, and all sorts of other things. And of course, it also tells you something about what last year was like and what you might expect, and you might expect in the next year. So one of the things we're really excited about is we're going to go back to the same place and make multiple measurements. So we'll see how this subsurface changed in 2025 and how that evolved when the new melt events come on top. The plot on the left is just a broader snow science plot. There's some subtle things in here. There's these density measurements that were made by hand. So those are hand hardness tests for the most part. And then I'm messing this up. These are the hand hardness tests in this histogram. The density tests are hand sampled. So you have your little snow cutter, you have a known volume, and then you measure the weight. And then the SSA, the moisture quantity, is measured with a little conductivity probe. And those three things give you some characteristics about the subsurface. And we did a total of 8 snow pits, which doesn't sound like a lot if you're a backcountry skier, but it wasn't the only thing we were doing. We were also building all of the instruments, and these are about 1.5 meter to 2.5 meter deep snow pits. So doing a snow pit was a full day activity. And we got a lot of great information from that. And we're validating it with our GPR. So one of our team members developed a ground penetrating radar in the 5 and 7 megahertz bands, so the microwave bands, and is working on relating the evolution of the GPR measurements that we took across the summer to the bookended snow pits that we took at install and removal of the instrumentation. I don't know if there are any radiometry geeks in the room. If you'd like the sun, raise your hand. Hey, we have a couple. Cool. This was really fun. And I'm really sad the cameras broke like a day before this happened. But check out this spike right here. So you have this solar curve where you come up to your about 800 watts per meter squared. And then this is this difference between the incoming and outgoing is your albedo. And then nighttime's coming. This is about 8 p.m. local time. So when you'd expect, according to the other curves, about 450 watts per meter squared. And we got a half-hour bump in solar radiation back up to nearly our solar maximum. Yeah, exactly. Optical waveguide sort of thing with the clouds. There's a bunch of stuff. I wish so badly we had a photo of it. Looking at the data coming in was really fun. We spent a whole bunch of time looking at like our different voltages and making sure there wasn't some power surge for a while, and a whole bunch of other theories. Aliens was posited by a few folks. They were like, this is just non-physical. It turns out that there is evidence for this in other Arctic conditions. There's some very specific cloud phenomena that can create a little waveguide and can collect light. And if you happen to be in an opening, you're the one that receives all that solar. What's very cool is you can see this response in the surface. So this is the surface long wave outgoing and incoming. So you get the sun input, and then the surface starts to warm up, and your outgoing responds. Your long wave, you start to radiate that energy back out. And you can also see it, I don't know if this plot, I'm going back. No, I'm not gonna. That'll take a whole bunch of time. You can also see it in our flux plates at the near surface. So you can watch the flux plate peak back up in the evening. Really interesting. And apparently this is called local solar enhancement if you want to search the literature for it. I hadn't heard much about it. I'm not directly a sun geek. I'm more of a cloud geek. But so a summary of our results from 2024. We did get to capture most of what we wanted to capture. We had a few issues. Cameras broke, a few other things. We had some power system issues at the very end that were really frustrating to me personally. But all in all, it was generally a success. We measured the full complete energy budget, the albedo, precipitation, moisture and hydrology, all of the things that I've been talking about for the entirety of the summer, which is very, very exciting for something that was a pretty ad hoc thing that was supposed to be a prototype. We were really prepared for a month or two of measurements and then dealing with moisture ingress problems and all of the other nightmarish things that could have happened. And then we definitely measured the macrophysical changes. So we're going to be able to write a firn paper. The snow scientists are working on a paper right now to hash out exactly how and why the subsurface evolved with the energetics throughout the summer, which is a bit unprecedented and certainly in autonomous operation in that detail. And it's super, super exciting. It's been a really exciting time being back. And then we've also put in a proposal recently to do the model evaluation we're talking about. So this grant was specifically to make the measurements, and now we have to decide exactly what we want to evaluate in terms of science. Okay, you made it with me. Thanks.
Thanks, Michael, for that really interesting, fun, and broad seminar. Do we have any questions from in the room? Quick reminder to those online, you can still enter your questions in Slido at the bottom of your screen.
Wow, this was really an awesome talk, and it brings back a lot of memories. I spent 3 summers on the Greenland ice sheet at Summit Camp, so never landed in Raven, but and you've done it. It's really fascinating to see these novel measurements there. Question that came up with, maybe you've measured that and you're geeking out on this, so I might ask that. Did you also look at, like at night, when you get clear nights, you get a lot of resublimation of the moisture during the day. Did you look at how the firn crystal structure changes near the surface? So the surface hoar formation, for instance, how that affects the albedo and long wave emission, and then also what it does to the mass budget, the mass balance of the surface.
Yes, this is a fantastic question, and I can tell you have the background for it. We did, and this is one of the things we're really excited to constrain. There's some asterisks on what we did. We knew we weren't going to get a vertical resolution in certain fluxes because we didn't have the time to develop it. And so constraining the mass budget in the subsurface is going to be kind of hard. But we've already put together a mass budget for sublimation. And it's really remarkable. And this is pretty well known because you can make these measurements at Summit. But we, down here where the air characteristics are different and the transport's different, and you also have sitting water sometimes, we were really surprised to see it looks like roughly 30 to 40% of the mass sublimates back into the atmosphere, which is a lot. At Summit, the number is roughly 15%. So it's like double maybe even close to triple the amount of mass that sublimates in the atmosphere. And people have, people have measured that in different ways, but the resolution and the constraints on the specific events is really exciting. And the macrophysical properties in terms of the evolution is really exciting. The GPR will constrain that. It's very much a research grade instrument. So there's a graduate student who's processing that GPR data and is trying to do exactly what you're hinting at. And it's really neat to watch. They've already made some really cool progress. And I'm really hoping if they can improve some of the signal processing, they could get a resolution on the scale of like 5 centimeters, which is really, really remarkable, and could do a lot of what you're talking about. So the transport downward and the crystal structure change and the densification.
Great question. Chris?
Great talk. Thank you very much. I was curious, your plot that was showing albedo and precipitation, it seemed like the albedo increased prior to the precipitation, especially some of the big events.
Yeah, there's some subtlety there. Part of it is that I just sliced these plots together, so it's not like exactly perfectly aligned. I hate to admit that. Because the data is at different processing stages, and I was in a hurry, as we all are. So that might be a bit of it. The other part of it is a lot of what happens before these events is about evolution. You get a lot of blowing snow beforehand, too. So you might not have snowfall that you pick up in your radar, in your rain radar, but you'll have snowfall that has been transported because, of course, if you're bringing clouds and snowfall, you're bringing in wind. And so a lot of that is about blowing snow. And we have some sensors that can get at blowing snow, and this is going to be a part of it. That's a really keen eye. There are some events, this one in particular is a bit of, it's not a mystery, but I know I was there, that this June event is really tied to blowing snow. And this one here in late July seemed to be less so, and you see the spike occurs quite a bit after it. Great look, though. Yeah.
So speaking of blowing snow, what were the issues with wind power?
All of them. The thing that killed the wind was actually not the thing that I expected to kill the wind. The bearings gelled eventually. We used cold weather grease. We repacked them with like a really nice, we got a bunch of recommendations from folks on which grease to use. And we did that. And the bearings, when we got back, had just completely gelled and seized and then oozed out and just died. That wasn't what we expected. That was what totally seized them. We also had some balance problems, so we had accretion and all the things you would expect. And we did our best to mediate that. They were black blades. We hydrophobically coated them. We don't heat them because that's its own engineering task, but you could. Yeah, it'd be fun to talk a little bit after. Have you tried to do Arctic? Yeah. We knew, I mean, it was probably the most intense argument we had as a team was whether or not to try the wind. And no one really thought it would work, but some of us thought we might learn something. So that was.
Did you have a follow-up, Chris?
And a completely separate question that was, it looked like your solar panels were deployed facing east, west, and south. I was curious why you chose that versus just a singular angle tilted towards the south.
Another great question. You're all asking great questions. A full south-facing solar array would be more efficient. It's the better choice in terms of, do you want to gather your watts most efficiently? There's some questions about how you balance that with the size of your battery pack. If you had a very small battery pack and then you had a moderately sized south-facing array, you might imagine your dips get bigger at night. And so you want to kind of mitigate that. That wasn't actually why we did the U-shape. We did the U-shape because we were really afraid of a specific array having a problem, either drifting over or freezing up more than the other. And it was more of a backup. So each one of them was wired independently, and each one of them operated independently. So had there been a broken panel in one, we would have still had the other two. So it was much more about redundancy than it was about efficiency in that way. I don't know if it was the right choice, actually, in the end, but that was the idea.
Great talk. I'm interested in atmospheric profiling, which you found out. Did the microwave radiometer detect inversions? For example, the CL61 ceilometers, we have 2 of those. And did you see things like ice crystals in the you didn't show any of the depolarization data, but that would have been interesting to look at.
I didn't because I didn't want to get into the weeds.
Okay.
Which is a shame because there's a really cool event, and I would waste a bunch of our time pulling up the dipole data. This clear sky event here, so it's not crystal stuff, but we did see some of that. But this is the easiest thing to point out. This was an aerosol transport event. So the CL61 has the sensitivity to pull out some aerosol stuff. And I'm not an aerosol expert, but I've read the papers. And I don't think you can be sensitive necessarily to species in a really interesting way. But we know this was an aerosol transport event, and we used some satellite data to validate that. And it was really cool. So there wasn't much advection at this point, and there was this aerosol plume that showed up, and it shows up really cleanly in the dipole data. So if I showed you the high resolution and vertical in time, I bet you'd be really intrigued by it. And this is one of the things we do want to look at. So it's a good question. I don't know yet. I haven't gotten back to it. We talked about it during the summer, and we actually pulled back the high resolution data because it was so interesting. And we were going to do a high split analysis and just haven't gotten around to it. It could have been, someone else had another theory. They thought it was smoke from Siberia. There was another one. I don't remember.
Another concern is, a little bit concerned about how you mounted the microwave radiometer in there.
Me too.
I suspect that you may be getting some bias from the frame of the system, and because looks like there's a metal pipe almost above it, and that's probably distorting the measurement somewhat.
Yeah. I should have just came and gave a talk before.
Yeah, that one, for example.
Yes. So I think there might be some biases, and we're going to try to suss those out. We did a couple calibrations before. We put it in the frame specifically. Why isn't that maximizing? Putting it in the frame was a logistical choice. We just have so much structure, and we knew we could keep it clean, and we had heating and such. Oh, come on. Oh, well. It's a little misleading because this is a really wide angle lens. So this bar is actually to this side of it. It's not directly over it. And the way that the radiometer faces is actually out the gate on the far side, and there's no pull over that. So I think we're okay-ish. I'm still on board that it's not my favorite way to do that. Yeah, I bet you're right. Yeah, a lot of what I could talk about this is making mediocre choices to make all of these things work together, and that was definitely one of them. Any other really good probing questions? Or from folks online. I don't know if I'm sure you're looking at it, but nothing yet.
I have another very exotic one. Have you, like, when you were looking at air temperatures near the surface, have you ever noticed any minimum temperatures that were elevated off the ground, that you actually measured the coldest temperatures, not near the surface, but up in the air?
Yeah, absolutely. And this is, yep, I can tell you've thought about a lot of this before. So we have a weekly meeting where we're discussing exactly how we're going to deal with what or how we're going to write up what you're talking about. Let me find the plot instead of trying to talk and find the plot. Yeah, there we go. So we intentionally set up this thermistor string so that, and the reason it's split up, and I probably should have said this when I showed you the plot, is this is the air. So at install, that line is where the firn was, and then you can watch snow accumulate. So you can see the snow goes up, and now the surface is probably more like right here, and eventually more like right here when you start to see the really heavy melt events. So these temperature sensors are actually air temperature. And at the cold times, it's almost always not the coldest at the surface. And the height that occurs at, and the reason or the different physical changes between the different nights, the statistical reasons, is a really cool thing. And there's a lot to suss out in terms of how and why models are wrong. I don't know if you're still working in this realm, but there's a guy, David Clemensoul, who just is doing a postdoc now, I think. Might be a research scientist now, who does 1D column modeling for energetics, and that is the question he wants to answer, is exactly that. Because if a model gets that height wrong and that like that, he was calling them micro inversions. This little
Elevated temperature minima.
yeah. If you get it wrong, it's probably because you're getting something else very wrong. Maybe the long wave budget, maybe the conductivity of the surface. There's a bunch of different things that could cause that. And so he thinks it's actually the best way to assess model issues on a thermodynamic level. So we've been poking at it. Unfortunately, I don't have a conclusion I can just throw your way, but it's a really interesting question. Yeah.
So you noted that your larger question was, what is the fully coupled climate where it melts? And you made one reference to synoptic conditions, but have you looked at the different synoptic conditions? I mean, you only have so much time here, but have you looked at conditions that really lead to particular things happening on the small scale like this that might tell us, as the climate progresses in the future, what's going to happen?
Yeah, I was kind of made for this question. My thesis was on statistically evaluating synoptic connections to these events. And my goal for this data is to do exactly what you're talking about. So we have, can I explain this in 30 seconds? I did this clustering algorithm where I identified clusters of important synoptic patterns. And then I linked those to events at the surface. So you might pick out certain patterns in here, like clear sky days or thick, moist cloud days, and then related those back to those synoptic clusters. And the cool thing is if you have the clusters, then you don't have to have this data every year. You could look at reanalysis or projections. You could look at CSM and say, okay, when do those occur and how and why, and do some statistics on it. And if you really trust things, then you could do, say, changes in climate or changes in synoptics. And it's very much on my radar. I think in terms of like global climate, that's with this research what you have to do. I haven't started that work yet. We're still processing the data, but it's very much on my mind.
So I did my PhD research in Antarctica on something very related to local solar enhancements.
Cool.
So could you flip that
Definitely. Very
just
cool.
so that I can talk to Sebastian about it later?
This is why being in Boulder is so fun. This is, yeah. I'm going the wrong way. So you don't think it's aliens? That's what you're saying? Yeah, and I would happy. This is actually our lower. A lot of the plots I make just for the efficiency are lower resolution in terms of I don't use our full 1 minute data. I have really nice process net CDFs. That's what we output on our real time side. So I could hand you the data for these 5 days, and like all of the skin temperature and whatnot if you were that interested. But I could also just send you the plot.
We get diffuse and direct too, so
We do, yes.
you can definitely tell whether, I mean, if it's direct, then it will definitely be odd, right?
Yeah,
And
yeah.
the instrument issue, so it must be the diffuse that's that is enhanced, right?
That's what it, yeah, and it's not in this plot for folks at home, the direct and diffuse, but we did measure it. And we looked at it together and it was diffuse, yeah. So wait, what's your hypothesis? Can you give her the microphone? You're saying is, do you think?
Oh, I thought you wanted to discuss it. So, yeah, I mean, so it's probably that you have like a stratiform cloud cover, and you have a lot of multiple reflections between the surface and the clouds that are bright,
Yeah,
and that will enhance your diffuse. And on the other hand, you get the increased long wave downward from those clouds that will also heat the surface.
mm,
Right? I mean, is that also your interpretation, or?
that sounds about right. I mean, that's what we talked about. Can I ask you a question?
Clear sky day and then a cloud come, at an angle.
Is that on the scale of what you would have typically seen down there, like that large?
It can happen. I mean, we measured, yeah, you can measure locally at a radiometer more than the incoming solar radiation in a column.
Yeah.
I saw that all the time in Antarctica. So then that would mean that is possible. It's just, it's weird that it's at that time of day and that it's that intense for me, but I don't know,
Yeah.
maybe not.
Well, and let's see. This is a good example of it, actually. Oh, why does that one maximize? The other one didn't. That's so annoying. This is actually facing the sun at almost exactly that time of day. And in Greenland in particular, this isn't a great example of it. There was often, let's see, that would be northwest, and we're closest to the west coast. You'd often, on the edge of the horizon, see that coastal stratiform cloud forming, just visually. And so I wondered if that was specifically related to it, but I can't make any claim. It was just something I was chewing on that might have made it that large.
Great. Well, I had one other follow-up question on an earlier question. You mentioned you had a disdrometer and someone who's going to look at some more of the microphysics. Did you have other in situ instrumentation?
We didn't actually have a disdrometer per se. We had the ceilometer, which has the dipole on 2 axes, so you can get some information about shape and habit. When I was talking about macrophysics, or microphysics of like the crystalline structure, I was meaning on the surface for our sampling measurements. We've talked about a distrometer, and we think we're going to deploy one next year for exactly that. We don't have anyone looking at it right now because, like everybody, we're a very small team, but it would be really neat. Yeah.
Cool. Well, if you decide to, let me know. We can chat.
Yeah, be happy to.
All right. Any other pressing questions? Great. Well, let's thank Michael one more time for that great discussion.
Thanks for coming.